that means that it's recording. Just by way of quick review, remember our force diagram here, FB and FE, just kidding, FE and FB. Wow, it's harsh. Wrong. You hear things hitting the board when people throw stuff at it. These two forces are canceling out, right? And all we did was just say FE equals FB, and then we got down to V is E over B, right? So we said EQ is equal to QVB sine theta, Q's cancel, we got V is equal to B. So that's how we did that. And then for the second part, we said if we look at QVB sine theta, if V goes up, then FB goes up. Right? And since FB is pushing down, if V is greater than E over B, then that's going to result in this thing curving down. Right? So that's the part I want to see. I believe I'm recording this. And then for here, we just said this velocity right here, as it comes out, must be E over B, because that's what we were told. And so if that's E over B, I just plug it in. FB is equal to QVB sine theta. Again, that goes away because everything's perpendicular. So I get Q is E over B times B. B cancels, and we get QE. And when we look at this, we can see that that is coulombs times newtons per coulomb, which matches with our newtons per force. Then we say describe the changes, if any, in the magnitude direction of the magnetic force as the particle moves in region 2. Okay. So now we have this thing right here going ahead with the velocity E over B. Velocity E over B. Brian, which way does that particle get pushed by the magnetic field? Down. Show me with your hand. Which way are your fingers pointing? I think your fingers are pointing at your face. Unless those aren't your fingers. Okay, right? Now what did you do with your hand? Okay, so it's at your face. So you see how this is dots? Now when Trini did this, she pointed these dots at her face. What's this? Dots or X's?
Something very blurry.
Oh, you can have.
It's kind of blurry.
Interesting. I don't know if it's out of focus.
It's simply just small.
Yeah.
It was like, it's just small.
Oh, that was out of focus. All right. Okay, now you can tell.
Yes.
Okay, so, all right, Brian. Hit me up again. Which way is it getting pushed? Up. Why? Okay, good. That explains it. All right, everybody cool with that? So, before, these were not discernibly different, so that's why Brian was pointing at his face. But he once he saw they were X's, he realized that's different, and so we get an FB of this way. Does that make sense? And again, how do we calculate that? We have FB is equal to QVB. Same thing. So then we have Q times E over B. Right, same thing. So it's just QE, but it's the force there. So it's moving at this is the force EQ that way, and it's pointed upward. All right, so yeah, so the magnetic field is going up. In this one, the magnetic field was pointing down. Okay, and actually in this one, you could say something like, but it said V is E over B, right? So then B in this one is E over V. So you could maybe solve for this B field and talk about that if you want. Wait, no, it doesn't say field. It just says force. Okay. Sorry. It didn't ask about the field. It's just asking about the force. So this force was pointing down, and then this force is pointing up. Yeah.
Wouldn't you not be able to cancel out the two D fields because they're different magnitudes, B1 and B2?
So this one was
They didn't tell us.
FB was equal to Q, and then this was E over B, and then this was
B2.
this is the other. This is B2. Oh yeah, good point. Okay, that's good. Good point. They didn't say whether they're well, clearly they're not equal because one's going into the board, one's coming out of the board. Excellent. So I should have labeled that B1. So this doesn't necessarily cancel. So I can't just say this is EQ. I need to say that's the whole thing. So I need to say that the whole thing is whatever. It's kind of like EQ, like B2 over B1. So I was off by a factor. Okay, so that's good. Then, good job. Part D, describe the path of the particle in region 2. So in region 2, this should do what? If it's pointed up, if the force is pointed up. Let's see. Van, what is this path going to look like? So show me what the force is doing, first of all. Okay, pushing it up. Now, notice, let's say that this is the particle right like this. When it goes in, it gets pushed up. Is this pushed up? Is this pushed up? Is this pushed up? What pattern is that? Yeah, circle, right? So you'd want to say something like, if it remains in the field, it's going to do something like make like a semicircle like that. Well, quarter circle. Of course, you could calculate that radius, right? And we could calculate that radius using the cyclotron equation, because if we're supposed to describe the path, we would want to say something like a quarter circle, and we want to say the radius. So we know the velocity when it hit here was E over B1, right? Okay, and then we know that mv squared over r is equal to qvb. That is the same v, so we can get rid of that. And we know that r is equal to qb over mv. Now this is b2. So then we can say r is equal to qb2 over m e1, and then b1's up there. So this gives us the actual radius of that travel. Now, if you look at part E without doing this for part D, that looks sort of intimidating. But if you look at part D and the answer for that, do you see how you can find part E? Look, right there. That's not a good highlighter code. That is what they're looking for. So for part E, they want Q over M. So all I gotta do is say Q over M is equal to R E1 over B2 B1. And then they gave you like a list of stuff that you could use as the initial definitions, and you just have to say what is on here that wasn't in that list. So if I go back and look, all right, so it was mass. We didn't know the mass of the particle. So in order to be able to come up with Q over M, oh wait, no. Oh, actually we need that. We knew E, we know B1, B2, B2. We wanted Q over M. And it's not previously defined. I think we had everything, didn't we? Yeah, I just said that Q over M was equal to something over B2, B1. RE? Okay, so you have to say R because you probably want to say that even though R was like determined in part D, it's not a given. So. All right, and that is that problem. Questions in general on that problem? The way that you have to attack these things is kind of just one step at a time. What are they? You know, what do I have? What are they asking for? It's just like the logic that I tried to teach you in the very beginning of the year. Well, not necessarily teach you, but sort of smashing your head and making you do a tedious problem. Okay, so then we should move on to 2010. This is a fun one. Okay. So does everybody get what's going on with this little car? So this car has a loop of wire on top, and then this car is going to roll into this magnetic field. Right? So it's going to roll in there. And when it rolls into the magnetic field, what is going to happen to the flux in that loop of wire? What is going to happen to the flux in that loop of wire? Evan. It's going to increase, right? And then once the loop gets in the magnetic field, once it's completely entered, what happens to the flux? What happens to, he said it's increasing. What happens to the flux after this car gets in here? Tiffany Chang. So it'll decrease once it's in the magnetic field. If we imagine that, but if you imagine that this is the loop, once it's in here, going from here to there, what will happen to the magnetic flux? Will it decrease? What's that? So how would you know that it's decreasing? Like what would visually, like how did Evan know that it was increasing? What's that thing with all the X's? What does that mean? Good. Into the board. And what are those X's? Excellent. So that is a magnetic field. And each one of those X's is like a little tiny, like, I don't know, you can imagine like a beam of light, right? So if I take this paper, and here's where it starts, right? There's a line on the floor. So it starts right here. And I'm standing here. How many beams of light are hitting my paper? None. What happens to the number of beams as I go here? Increasing. Now, let's say that the beams are all the way to 0. Okay? So it's all the way to him. As I'm walking like this, what's happening to the number of beams that hit this? So if you look at that, you see the pattern of the X's? Does any of that look unevenly spaced? Yes, very good. You see, because the density of that magnetic field, and kids, you will not face magnetic fields that change, right? Like when you become young adults in college, if you pursue science, you will face magnetic fields that change, right? And it's not that bad. It's like a double or triple integral, but whatever. So our fields are always pretty consistent, all right? They're always consistent. So when I'm going through here, does it make sense that the number of dots that hit my paper will always be the same? Does that make sense to you? The same dots aren't touching the paper, right? Because these 4 dots aren't touching my paper. Now they're touching, and now they're not touching anymore. But when these 4 left, what happened over here? Yeah, 4 more. So if there was 30 dots touching this paper, no matter where I go in this field, as long as I stay perpendicular, I'm the same. Does that make sense, Deborah? Okay. So, so we're going to get some increase in flux, and then we're going to have constant flux inside of here. Okay? just a little observation. All right. So on the figure below, indicate the direction of the induced current in the loop. So do this on your paper somewhere, on your notes or whatever you got in front of you. Do it there. Anybody need more time? All right. So let's see. Jackie, well, before we do that, can Andrew give us Lenz's law? Pretty simple, right? Fight the change, okay? Fight the change that Evan said is increasing, and it is increasing into the board. So, Jack, which way is the current? Okay, so what I do like is what Jackie's realizing is that if we're gonna fight the change going into the board, then her fingers need to point out of the board. Is she correct in this? Is everybody cool with that? So now, let's pretend like my hand is that ring. So put your fingers out of your ring. So I'm sticking inside the ring. Yeah, there you go. Now look at your thumb. Which way is your thumb pointing? Clockwise or counterclockwise? Counterclockwise. So Jackie's answer is counterclockwise. Is she correct? I think so. Right? I think she's right. So good job. Right, so once again, the flux is increasing. So there's always two things you have to pay attention to. The flux is increasing into the board. So when you fight that change, you have to flip the switch and do the whole thing. So you need to you need to try to put your fingers out of the board. Right? You always have to fight whatever change is happening. You know, if this was decreasing into the board, then you would have to fight the change of the decrease. Okay, but that's good. So she got that right. Excellent. Alrighty. Now, when the front edge of the rectangular loop is at 0.12, so what we're saying is 0.12, so right on here. So if it's 0.12, that means this is 0.08, still sticking out. Is that okay with everybody? Does that make sense? Okay. And then, of course, it's going to have to shift. So when it's 0.12, its speed is 3 meters per second. Calculate the following for that instant. The magnitude of the induced current in the rectangular loop of the wire. What? Oh. It's 0.1. Yeah. So, let's see. Otis, what is Faraday's law? Yeah, negative delta phi over delta t. Yes? Does this make sense? Negative delta phi over delta t. So, we say, and then, so if Lenz's law says it's negative delta phi over delta t, and then I is v over r, or this over r, I hope they give us a resistance. We'll see. Then we can like start plugging this stuff together. But let's take a look. see if they give us the resistance. Oh, yeah, there you go. 4 ohms. Excellent. And the field is 2 Tesla. All right. I can still see the information. So we have I is equal to the EMF over R, and the EMF is negative delta phi over delta T. And then for that delta phi, the B field is not changing, it's the A that was changing, and the cosine theta is fine. And then we just have to find the amount of time that it took to get in there, right? So how long, they said this was moving 3 meters per second, and it traveled this far into it. Please tell me that there's a constant speed. Didn't really say. They just said at that point. We're going to assume it's a constant speed because that would be a pain in the butt. So, yeah, the B is 2 Tesla. The area is 0.12 times 0.1, so that's 0.012 square meters. And the time that it took, this is V is x over t, so t is x over v. So this divided by 3, which gives you 0.04 seconds. Questions? Yeah. Oh, this like, here we go. Let me draw it like this. It's kind of like this part, like that, is in the magnetic field. And then they told us that this distance right here was 0.12 meters, and we know that this height is 0.1 meters. So I just multiplied the two together. That's fine. Ask any questions that you need to ask. Okay, so this becomes 0.024, so that's like 2.4 divided by 4, so it's like 0.08 or something. Oh, how terrible. Hold it. Oh, yeah, that's 24. So 0.06? 0.6. Yeah. Okay, so that's 0.6, that's volts, or negative 0.6 volts. When we plug that in there, divide it by the 4 ohms, then we'll get a current of negative 0.6 volts divided by 4. So then 0.15. So 0.15 amps. Or negative 0.15 amps. So again, you use Faraday to get the EMF, then you use Ohm to get the current. That's how we find that answer. Then the magnitude of the net force on the loop. The net force on the loop. What could be causing the net force on the loop? Kevin, any help? Any thoughts? Okay, how about this? Can you tell me the 2 right-hand rules, please? Say that again. Okay, what does this one mean? Good. What's this one mean? Okay. What? Magnetic fields push charges? Magnetic fields push moving charges. That's key. That's super important. Kevin, are there any moving charges in this situation? No. What did we just calculate? In part I, what did we just calculate? Current. Here's a current. Aha. Do you see what we're doing? Okay. So Ray, which way? Now, what did? Let's see if you were paying attention to your classmate. Which way did Jackie tell us the current was going? Counterclockwise. So on this side, right there, which way is it pointing? The current. On this side, right there. Up. Okay, it's pointing up. So show me. And which way is the magnetic field pointing? Yeah, it was into the board. It's up there. But yeah, I'm not testing you. I was checking to see if you remember if I needed to pull it down. So show me with your right hand what's going to happen. Magnetic field's into the board. The current is pointing up. Which way is that going to get pushed? To the left. That's why That's why they asked this problem. Get it? And then that's pretty easy, actually, right? It's just F is equal to BIL. So that's 2 Tesla. Oh, what's our current? 0.15. Okay, 0.15 amps. And then the length was 0.1 meters. Then C, at a later time, the current and loop were completely inside the magnetic field. Determine the magnitude of the net force on the loop. The net force should be branch. Alvin, what do we do? Yeah. 0. Why? Do you remember my conversation with Tiffany? Once I'm in the loop, you notice what Alvin said. The flux isn't changing. Once I was inside this area, my little paper had a constant number of dots, which means it's a constant amount of flux. If there's no delta flux, then there is no what, Nelson? According to Mr. Faraday. Oh, it's Friday. I should give you a photo. Yeah. What's that? Okay, so understand, Mr. Faraday talks about EMF, right? Right here. If there's no change, if there's no change in flux, then there is no EMF. And if there is no EMF, then there is no current. Get a piece of paper. Let's go.